screen. Okay, so thanks a lot for the invitation. It's really a new experience for me, sitting in my office in Prague and giving a talk in Shanghai in the afternoon. So I enjoy it. On the other hand, I must say I don't have too much experience with this long distance talks. In particular, I'm usually have problems with time. So either I finish too early or I hope not to finish too late. But I know there are 2 more talks, so I should finish at least before the next talk starts. Okay, so this is a joint work with Francesco Fanelli from Lyon and Martina Hoffmanova from Bielefeld. And I apologize, the title is a little bit ambitious because at the end of the day, you will see I don't really have some kind of satisfactory ergodic theory for compressible fluid flows. However, this is just the beginning. To the best of my knowledge, there are not so much, not so much is known in this field. So let me start with some introduction to the problem. I will start with a general framework. I emphasize that I will speak about what I call energetically open system. In the field of fluid mechanics, this means that somehow the system interacts with the neighborhood through the boundary, which is not usually the case in the literature. In the literature, when we speak about fluid mechanics, at least in the mathematical literature, they study either Euler or Navier-Stokes equations. Actually, in my talk, I will also study, or I will also consider Navier-Stokes equations. But usually, they don't pay too much attention to boundary conditions. Usually, the most popular boundary conditions is what is called no-slip boundary conditions, which means that actually the fluid is energetically isolated. So from the point of view of, say, long-time behavior of the system or, say, description of turbulence, this is a very boring scenario because all these forces or all the influence of the outer world comes only in terms of the initial data. So let me remind you the famous saying of Clausius, which can be applied entirely to fluid mechanics, which means the energy of the world. He says world, but here you should understand world as a closed fluid system. So the energy should be constant because that's the first law of thermodynamics. The system is isolated, so its energy is constant, and its entropy tends to a maximum. Well, from the practical point of view, this actually means that the solutions of such a system tend to equilibrium solution when time goes to infinity, and that's very boring. And I will show you an example that this is indeed the case. On the other hand, if you consider energetically open systems that somehow exchange the energy with the outer world, then there is something what people commonly call ergodic hypothesis, which means that taking time averages of trajectories of the flow is somehow equivalent as taking some average with respect over all initial data or possible states of the system with respect to some probability measure. And well, that's of course a hypothesis, and it's extremely difficult whether or not this holds for specific systems. So mathematically speaking, for closed systems, we have this very boring scenario, which is written down on the slide. So, so the solution tends to equilibrium when time goes to infinity, and typically this equilibrium is uniquely determined by the initial data. I mean, the system may admit more equilibrium solutions, as we shall see. However, each solution will tend to equilibrium when time goes to infinity. For open system, on the other hand, it makes sense to take the time average. So U is just the abstract say trajectory representing the vector of state variables of the dynamical system. Then you take a Borel function f, you apply to U, and you consider this average, and you somehow hope that this average will converge to a number, and the number is actually given as the integral of the function f over some measure, which is then called like ergodic measure, or the measure which characterizes the behavior of the system in the long run. And if this holds for any, say, Borel function f, then the measure somehow characterizes the behavior of the system. And so in my talk, I will focus on the second possibility. So let me introduce, to introduce the abstract setting, I will introduce the space of trajectories. So in my case, what I mean by trajectory, by solution of the problem, will be what is called entire trajectories. So these are solutions which are defined for any time, not only, I mean, usually one considers the initial value problem, and solutions are defined for times from some specific t0 when the system starts to move to say plus infinity. However, in my case, I will consider what is called entire trajectories. They will be defined for any real time, and they will range in some abstract space X. And I will also consider the omega limit set of a given trajectory, which starts, say, at the time 0 from some point x0. And the omega limit set is actually the set of all limits when I consider sequences of time shifts going to plus infinity. So it turns out that actually the omega limit set, if it exists, then it is contained in the space of all trajectories. And of course, in order to say something about its existence, you have to say something about compactness of the trajectory space. Now, if I have this omega limit set, I will show again everything on the example of compressible Navier-Stokes system. If I have an omega limit set, which is the set of solutions defined on the whole real line, I can also consider what is called sometimes stationary or statistical solution. So by definition, stationary statistical solution of the problem is actually a process. Stationary, it's a stochastic process going from R, so it's defined for any time t. It ranges in the space of trajectory, so it is continuous with respect to time almost surely, because it's a stochastic process. And we say that it is a stationary solution if the stochastic process is stationary in the sense of the definition of stationary stochastic processes, which means that if you take its law, roughly speaking, its law is time shift invariant, which means if you take its value at a given sequence, a finite sequence of times, and you shift it by time, then the joint law of all these of the whole entity is the same. Or you may equivalently formulate it in terms of the omega limit set, or in terms of entire trajectories. If you consider the law as a probability measure on the set of entire trajectories, then it is shift invariant. And we also require that this V solves actually the associated evolutionary equation, the associated problem, almost surely. So this is what is sometimes called stochastic stationary statistical solution, and it is closely related to the concept of the ergodic measures, as I hope I will explain it later. Okay, so how do you construct these stationary statistical solutions? So assume that you have a trajectory, which is a trajectory U. Assume that the trajectory exists. Know that actually I don't need any kind of uniqueness, which is the point here, since I work in the space of trajectories instead of working in a fixed phase space. I really don't need any kind of concept of uniqueness for the dynamical system, which is important in particular in the context of the Navier-Stokes equations, since I want to speak about global in-time solutions. And for Navier-Stokes equations, we know that global in-time solutions usually do not, I mean, they are not known to exist for a long time. So I will have to work with weak solutions that, on the other hand, are not unique. However, in order to develop all these concepts, I don't need any uniqueness. Okay, so so we consider the what is called ergodic averages sometimes. So I consider this trajectory as being a kind of a measure, and the measure is represented by the Dirac mass, which is actually sitting on the trajectory. Then I take the integral over time from 0 to capital T, and I normalize it by dividing by capital T. So this is a probability measure, right? Because I mean, delta is a probability measure, so the whole thing is a probability measure. And now I want to see the limit when time goes to infinity. And this is the so-called Krylov-Bogolyubov construction that assures that if you have tightness of these probability measures in the space of trajectories, then tightness means that basically all these measures are sitting on a compact set in this context, because these are Dirac masses. So, well, not exactly. I mean, tightness means that you are sitting compact set with the exception of a set of small probability. However, in my case, all solutions, actually all trajectories will be sitting on a compact space. compact set, and then the limit then you can pass to a subsequence Tn which goes to infinity, and then this subsequence will generate a measure on the space of anti-trajectories. And this measure represents actually if you endow the space of anti-trajectories with this measure, then you get stationary statistical solution in the sense of the previous definition. Now the ergodic hypothesis can be reformulated in the sense that actually this mu, the measure mu, is unique. And so in particular, there is no need to pass to subsequences. And the whole sequence, like the whole time integral from 0 to t divided by capital T converges to the measure. And the measure, well, unique means, of course, we will see that the measure has no chance to be unique for any trajectory for normal dynamical systems in fluid mechanics. However, it should be unique on the omega limit sets. It's a measure that sits on the omega limit sets. This can be easily shown. And well, the ergodic hypothesis tells us that actually the measure should be unique on the omega limit set. In terms of stationary processes, there is only one, I mean, there is all stationary processes sitting on the omega limit set are equivalent in law. They have the same law. This is just reformulation of the ergodic hypothesis. Well, in my talk, I will be less ambitious. So as we see, actually, the existence of the stationary solution or the satisfaction of ergodic hypothesis concern the existence of this time or of the existence of the limit of ergodic averages. I will formulate something what we call weak ergodic hypothesis, which means that actually the limit when time goes to infinity of this average exists, meaning exists in the sense of narrow convergence of measures. And then again, the limit generates a stationary statistical solution. Of course, even in this case, I will not be able to show that the weak ergodic hypothesis really holds for the Navier-Stokes system. However, I will be able to show that at least on some particular sets, it is satisfied. Okay, so I apologize for this long introduction. Now let's turn to the problem. I will explain why I do everything for barotropic Navier-Stokes and not for the traditional incompressible Navier-Stokes. Actually, sorry. Actually, it turns out that barotropic Navier-Stokes is much closer to what I would call energetically closed system. The energetically compatible system with respect to the law of thermodynamics. And so I think it's more convenient or more physical to consider this one. I will show you later that actually all these concepts that are being used in the context of incompressible flows or attractors and similar objects is not really meaningful in the context of thermodynamically consistent models that also take into account compressibility and also the changes of the internal energy. Okay, so let me describe the problem for those who might not have seen it before. So this is a simple model of a compressible fluid. The fluid is described by the density rho and the fluid velocity u. And the first equation is the equation of continuity, and the second equation is the momentum equation. And the fluid is driven by some driving force G. Actually, in practical, S is the viscous stress tensor, so it's a Navier-Stokes system. It is given by Newton rheological law. So I consider Navier-Stokes system, which means Newtonian fluids. And so there are two viscosity coefficients, mu and eta, and mu is supposed to be strictly positive, which means that the fluid is really viscous. And the pressure here, it's actually an explicitly given function of the density rho. Well, in most of the cases, the most popular example of the pressure is the pressure which is given by the isentropic state equation. So the pressure is just rho to the power gamma, where gamma is called adiabatic exponent. Actually, the forcing term here, well, in general, of course, people like to take objects that are general, but actually, I know only about one, say, meaningful external force that can be, or this is like volume force that can act on the fluid, and that's gravitational force. But the gravitational force is a very specific force, which means that it is actually a gradient of some function f, and the function f is just a function of x. Sorry, that is a typo. There should be capital F here. Okay, So if I introduce G in this form, then the whole thing, the whole system has the energy. The energy function can be written in this form. Now here M, it is more convenient to write it in this form in terms of the momentum. I'll explain why. So the energy is a function of rho and the momentum, M, which is rho times U. And it's a function of rho, represented by the so-called pressure potential, capital P, which is related to the small p by this equation. And if the force is present of the gradient type, then you should add to the energy a term which is proportional to rho times F. Why it is more convenient to write the energy in terms of M and rho? Because in these variables, it is actually a convex function of M and rho as a convex function of a couple. Actually, in order to have this, you need the pressure to be an increasing function of the density, which is of course the case for the pressure which is given by isentropic equation of state, but you may consider more general equation of states. As soon as you know that the pressure is an increasing function of the density, then this capital P is a convex function, as can be checked by just differentiating this equation. And the whole thing is actually a convex function of rho and M. If I consider U as a state variable, then it is not a convex function. And as we know, convex functions have good properties. In particular, since I speak about weak solutions, and convex functions are weakly over semi-continuous. So typically, for compressible Navier-Stokes, the good variables are not rho and U, since U, unfortunately, does not enjoy really any continuity with respect to time if you speak about weak solutions. What is weakly continuous with respect to time is M. So in order to build up a kind of dynamical system theory, which is necessary for the application of these ideas of the ergodic theory, you need something that's continuous in time, and that's rho times U and not U. And that's why also it's more convenient to speak about the energy expressed in M. Okay, so that's a problem. Later on, I will comment on the mathematical theory. We know I am interested in this system in the multi-D setting, in particular in the 3D case, which is the physically relevant one. We know that in general, the existence of solutions, I mean classical solutions of the problem, is an open problem. What is known is that classical solutions exist locally in time for any initial data, I mean physically relevant initial data, and they exist globally in time if the initial data are small. That's everything what we can say. So from this point of view, the system shares the same properties with the incompressible Navier-Stokes. You also have the existence of weak solutions under certain conditions I will mention later on the pressure term. The weak solutions have the advantage that they exist globally for any, say, large initial data, which means they represent a convenient object for developing any kind of long-time behavior theory. Well, the problem, of course, with the weak solutions is that they are not in general known to be uniquely determined by the data. And typically, in the light of the recent results provided by the convex integration theory in the framework of Euler system, we do not believe that the weak solutions are unique even for Navier-Stokes. If you want to say uniqueness, you have to add some kind of entropy condition, or if you want energy inequality, which I'll actually do later. Okay, so that's my system. Now, what happens in the boring, closed system scenario? So in my context, now the system is closed. So I consider everything in a bounded, sufficiently regular domain. I mean, regularity of domain is not an issue in my thought. And I assume that the boundary is isolated. I mean, which means that actually it's impermeable, which means that the velocity is tangential to the boundary, u dot n is equal to 0. But I also assume what is called no-slip conditions, which means that also the tangential component of the velocity is equal to 0, and so the velocity vanishes on the boundary. So the system is completely isolated from the outer world. And indeed, now the long-time behavior is what you expect, and what can be really proved is the Clausius scenario. Well, for the first observation, and let me point out that actually, I mean, what I'm saying now holds also for the weak solutions. It's not only for strong solutions. So independently of the problem of uniqueness, the weak solutions basically stabilize to equilibrium. So you can check that actually the total mass of the system, which is the integral of rho over the container, is actually equal to a constant. It doesn't change in time, even for the weak solutions. And the total energy, which is E integrated over omega, actually in this case represents a Lyapunov function because it satisfies, well, formally it satisfies energy equality. However, in the context of weak solutions, we usually prescribe energy inequality. However, this term, which is due to dissipation, is actually non-negative, as it can be checked directly. And so the energy is actually a non-increasing function of time. So in particular, the energy has a limit when time goes to infinity, which I denote E infinity. And now the system will stabilize to a stationary solution. I mean, basically you can see that in the limit, this integral should vanish, which more or less suggests, and it can be really checked, that actually the limit momentum or the limit velocity will be zero, while the limit density will be represented by rho infinity. If you plug in 0 in the equations, you will find out this equation here, that the gradient of the pressure evaluated at this limit density is equal to rho infinity times the gradient of F. Of course, this equation has a lot of solutions, as it can be checked directly. However, if you prescribe the mass and also the energy, because this solution should in particular have this energy and this mass, then usually there is a unique solution, and so all weak solutions will converge to this unique solution. Actually, it's not always true. It depends on the shape of the functional f. So if f, roughly speaking, if you think about f like being gravitational potential related to some object, which is out of the fluid, for instance, then if there is a single object, or if, roughly speaking, if the level sets of f are connected, have connected components, all level sets are connected, sorry, f is the gravitational potential, it is not the force, gradient is the force. So if all level sets of f are connected, then you can show that actually the problem has a unique solution with respect to this constraint. If you have sets that are not connected, then in general, you cannot prove a uniqueness of solutions of this problem. And in that case, we are also not able to show convergence. We only know that, well, the set of the omega limit set actually in this case consists of all equilibrium solutions of this type. However, we are not able to show that they converge. However, still, if you admit that, well, there is only one equilibrium, then all solutions converge to equilibrium. From the ergodic point of view, I mean, there is only one, the only stationary solution is the equilibrium solution. It's not only a statistically stationary solution, it's deterministically stationary solution. It's a static solution independent of time. And so we cannot see any turbulence. The corresponding ergodic measure is the Dirac mass sitting on this solution. Let me point out that somehow people believe that, well, this can be made like more real by imposing some driving force here. I mean, before I assumed that the driving force is very simple. The driving force was actually a potential of a scalar function, which was independent of time, and so the scenario, so the system was energetically isolated. So let's consider the same kind of boundary conditions, but now instead of the previous system, let's consider the full system. Sometimes this is called Navier-Stokes-Fourier system. I will not go into details because there is a whole theory, of course, mathematical theory for the problem here. I will just assume that, well, you are basically familiar with that. I mean, it's formally the same as the previous system. However, now you also take the temperature into account and you add the energy balance as one more equation. So you have like 3 equations. That's the first one is conservation of conservation of mass, conservation of momentum, and conservation of energy. And according to the specific shape of S and Q, which is the heat flux here, the system may be called Navier-Stokes-Fourier system. And let me impose again conservative boundary conditions, which means that the system is again isolated, which means the U is again 0 on the boundary. and the heat flux is also zero on the boundary. So the problem is again isolated from the energetic point of view. And now actually we will see that there is no G that would sort of mimic some complicated dynamics. Actually, if you consider G being a function of X, then there are only two possible scenarios. That's a result we proved a long time ago with a colleague of mine, Hanna Pesseltova. So if G depends on X, you cannot observe anything like complicated dynamics because there are only two possibilities. Either G is a gradient of some scalar function f, depending only on X. And in that case, the scenario is the same as on the previous slide as for the barotropic system, which means any solution converges to a static equilibrium as time goes to infinity. Right? So again, we don't see anything interesting from the dynamical point of view, or G is not a potential, and then the energy of the system becomes infinite. I mean, you may wonder how this is possible. I mean, that's very simple. That's a consequence of the second law of thermodynamics. You have an energetically isolated system, so the energy is not allowed to get out of the system. However, you pumping energy in because of this force. Well, according to the Clausius scenario, all the energy is finally converted to heat, and since the heat cannot get out, the energy is increasing to infinity. So in particular, this doesn't make too much sense to study, for instance, attractors for such a system. And this system is indeed a kind of real system since it includes all basic physical principles. It's the simplest possible complete model. Okay, so these two examples, well, you can go even further. That's the work we did with Dominic Bright. You can consider the same system, which means Navier-Stokes-Fourier, which is now driven by a stochastic force. So there is a white noise. Unfortunately, only in time, which is imposed as a driving force in the momentum equation. You take the same boundary conditions. Now you might be interested in really statistical stationary solutions, because in this case you do not expect to get like deterministic stationary solution independent of time. However, the fact that the system is energetically isolated gives rise to a rather, I would say, unpleasant conclusion that actually the system admits a stationary, I mean, everybody would expect that such a system, if it's real, should expect some kind of statistical stationary solution. However, this is the case if and only if there is no noise. So if there is a noise, simply the system does not admit a statistical stationary solution, does not admit stationary solution in statistical sense, which is rather surprising, which shows that actually if we really want to see something interesting in the long run, then we have to abandon the idea of conservative boundary conditions, at least for systems like compressible Navier-Stokes or Navier-Stokes-Fourier system. So I hope these two examples convince you sufficiently that if you want to see something interesting or something which is physically relevant, you should pass to non-trivial boundary conditions. So let me remind you, this is again, I'm repeating one of my previous slides. I go back to barotropic Navier-Stokes system with this energy, and let me go to what I call energetically open system. In this case, you just impose the in and outflow boundary conditions. So you assume that now the velocity is no longer zero on the boundary, but it is a given velocity field. Of course, in general, you may consider a kind of velocity field which also depends on time. However, for the sake of simplicity, I will assume that UB, the boundary velocity, is independent of time. So it's only a function of x. And I also assume that it can be extended to the whole domain omega. Right? And now according to the behavior of this boundary flux, I can divide the boundary into two parts. One is called like gamma in. That's the part where somehow the fluid comes in, because remember, n is the outer normal vector. So when the scalar product here is negative, the fluid is coming in. There is influx on gamma in, and on gamma out is the remaining part when simply the scalar product is non-negative. I mean, I do not want to go into details about the existence of the normal. I will assume that my domain is smooth, so I can have always outer normal. However, everything can be generalized. And now the density, or if you want the pressure in the context of compressible fluid, I mean barotropic fluid, can be also prescribed, but only on the inflow boundary where the characteristics, remember we have the first equation for the density, which is a kind of transport equation. And when the characteristics come in, which means on the part of the boundary gamma in, then you can prescribe also the boundary density, right? And so this is now my new problem. Now, if I write the energy balance for this new problem, sorry, which is here, well, with the modification to inequality in the case of weak solutions, then you see that actually it is much more complicated than for the closed system. In particular, there is some forcing there on the right-hand side of the energy balance, which depends on UB, which is the boundary velocity. Of course, this term would not be there if the boundary velocity was 0. And there is also this term, which depends on the value of the density of the boundary. So now it is completely clear that, well, the density is, sorry, the energy is no longer a Lyapunov function, and you get a more complex behavior, right? So that's my problem. Now, so what can we say mathematically? So first of all, do we have globally in time solutions? Actually, yes. I mean, there is a theory for compressible Navier-Stokes that was actually originated by the work of Pierre Lurion, later developed by many other people. Actually, at the beginning, the theory was built up on the hypothesis that the system is isolated or even periodic boundary conditions. However, everything can be extended to inhomogeneous boundary conditions. Actually, the available results are results that I mentioned here. So these are people of Korean group in collaboration with my friend Antonín Novotný. So we can say that we have weak solutions that do satisfy the energy inequality, which is important for the long time behavior. So of course the weak solutions are not known to be unique, but as I say, this may not be an obstacle when you study the long time behavior. So we know existence. Now, of course, if you want to study the long time behavior, you want to make sure that the energy, now we see the energy is not a Lyapunov function. So we do not know if the energy remains bounded. And of course, if the energy is unbounded when time goes to infinity, then there is a little chance to say something about the long time behavior. So we are interested in trajectories for which actually the energy, the total energy of the system remains bounded. If you go back, let me go back to the energy inequality. This is a non-trivial problem because here it's not obvious how to use, unless of course UB is 0, then it's not obvious how to use, for instance, some Gromwall argument to make sure that the energy is bounded. But something can be said in a joint paper with Francesco and Martina Hoffmanova. We actually proved that the energy remains bounded under some assumptions on the boundary velocity UB. If you slightly change the pressure law, then recently we showed with Jan Březina and Antonín Novotný that actually you can make sure that the energy actually remains bounded for barotropic Navier-Stokes for say large value, large amount of large set of initial data. What is more, actually, this E infinity constant here is actually independent of the initial state of the system, which somehow in the terminology of dynamical systems is called the existence of a bounded absorbing set. So for the system, even with the inhomogeneous boundary conditions, there are situations where trajectories are bounded. So from now on, I will focus on bounded trajectories. And I will define the omega limit set. So, so now what is my trajectory space? Now my trajectory space, as I said, it is convenient to work with the momentum and the density because these are quantities which are weakly continuous. So I can speak about their values at a specific time t. And I assume actually that the pressure is given by the isentropic relation. So it's rho to the power gamma, where gamma is bigger than d over 2. D is the dimension. I mean, that's a technical condition which I basically do not need in the analysis so much. I mean, in the analysis of bounded trajectories, because for bounded trajectories, actually, well, But however, it is needed for the existence theory. So without this condition, the system is not known to admit the global in time weak solution. So that's a technical condition. As far as I know, you can go up to, in the two-dimensional space, of course, the critical value of gamma is 1. You can go to up to 1 in the two-dimensional space. However, in the 3D case, that's the best result so far I'm aware of, like global existence of weak solutions. So now the trajectory space, I mean, this value, so the density, of course, the pressure is now bounded. So the density belongs to the space L gamma, which is exactly this gamma. And it can be shown that the momentum belongs to this LP space with this exponent, which happens to be bigger than 1 and less than 2 always. And so this is my trajectory space. Now I say that I would like to show compactness. Actually, in order to show compactness, strangely enough, I can stay in the space L gamma for the density. The density actually turns out to be compact in the energy space. However, for the momentum, I have to leave this strong topology of this space. Actually, I should go to the weak topology of this space, then everything would be fine. However, spaces with weak topologies do not have good properties from, say, the analysis of stochastic phenomena, since LP space with weak topology is not it's not what is called Polish space, and so it's better to work in a Polish space, and for that reason I just replace this by some negative Sobolev space with sufficiently big k. So my momentum is supposed to range in this. And now actually the whole everything what somehow makes it possible to say something about the ergodic hypothesis is represented by this general theorem we proved with Francesco Fanelli and Martina recently. So let's consider the omega limit set in this space, right? So the space is the space of functions which are locally continuous on the whole R ranging in this product, rho and n, and you can consider the omega limit set in this space. So the first observation is that the space is non-empty, which somehow is. I will show you on the next slide what is the crucial observation. For this, you already need some kind of compactness, because how do you prove it? I mean, you take a sequence of time shifts and you want to prove that the time shifts are strongly converging to some limit. So the space is non-empty. You can also show that it is compact in this space. It is shift invariant, and it consists of all globally defined weak solutions of the Navier-Stokes system. And in order to have this result, I mean, based on this result, I can show something about ergodic averages and other things. The essential feature of the proof of such a result is compactness of the densities. As you know, the density actually satisfies the equation of continuity where there is no dissipation there. There is no Laplacian of the density. So a priori, the density is not known to be compact. However, there is a beautiful idea going back to Pierre-Louis Lyons that actually using a certain quantity, which is called effective viscous flux, you can show that the fact that the density and U together satisfy the system of Navier-Stokes equations make the density compact. However, there is one point in the existence theory which is necessary for this, which is compactness of the initial data, thinking about a sequence of solutions. If you want to prove compactness of the density, and it seems completely natural because you have a transport equation for the density, if you want the density to be compact, you need the density to be compact at some specific time. Now, since we are speaking about global trajectories, trajectories defined on the entire line, we don't have any compactness a priori of densities at any specific time. So the proof of compactness of the omega limit set is not the same as the proof of compactness in the existence theory. So the crucial observation is that actually you define the quantity dt, which is a kind of defect measure. Actually, you take a sequence of time shifts and you define its weak limit, which is, well, for technical reasons, I take this convex function. It's not only for technical reasons. I mean, that's the only one for which the theory works. And I take the limit of this sequence. This sequence has a weak limit. denoted by bar. And since this is a convex function, it's greater or equal than the superposition of this function applied to the weak limit of rho's. And now taking this quantity, this is a non-negative function. Now you can show, which is a little bit lengthy proof, is that this quantity actually satisfies a kind of differential inequality. This, you can show that this quantity is defined for any time in the limit, if you take a limit of solutions. And actually you can show that this quantity satisfies this differential inequality. If you don't like inequality, you may think about the differential equation. So it's a bounded solution which is defined on any time on the whole real line. It is bounded on the whole real line. And this function psi here can be shown to be something which is like identity. So it's something which is 0 is 0 and it's positive and z is positive and negative and z is negative. Well, actually it turns out that if you have an entire solution of such a problem, then it must be 0. I mean, a bounded solution defined for any time of this problem must be 0. And so this quantity must be 0. And so this means that the convergence is strong. So that's actually the new ingredient which is involved in the proof of compactness of the omega limit set. Well, once knowing it, you can pass to Kirov-Bogolyubov method. So you take the ergodic averages and you take the Dirac masses sitting on the trajectories, and you can show that in the space of trajectories, actually up to a subsequence, this sequence of measures considered as measures on the space of trajectories converge narrowly to some measure, where the measure actually is, or if you want the space of trajectories endowed with this measure represents a statistical stationary solution. You can show that the marginal, which is just restriction of this measure to each time, is actually independent of time. So it's a kind of stationary measure, although we do not have really like semi-groups. So the point is that actually the measure is sitting on the space of trajectories, because the Kirov-Bogolyubov method requires something like continuity of the mapping in question. And so in the space of trajectories, of course, the mapping is merely a shift, which is a continuous mapping. If I work in the space, in the phase space, then I would need uniqueness or kind of Feller property for the semi-group, which I do not have. Well, now you apply what is called Birkhoff Khinchin Ergodic theorem, which tells you that actually, knowing this result, you can take a Borel measurable function on the space X, and you take the ergodic average, where this rho and m now is a function which is sitting in the omega limit set. So it's an entire solution defined for any time of the compressible Navier-Stokes system. You take a Borel function and applying the Birkhoff Khinchin theorem, that since this is a stationary solution, you can show that actually the limit of this quantity exists. So at least on the omega limit set of any bounded trajectories, we have what we may call weak ergodic hypothesis satisfied. I mean, let me point out that related results were also obtained for incompressible Navier-Stokes in the context of equations with stochastic forcing by Flandoli-Gatarek and Flandoli-Romito, Konstantin, Voyage-Manni-Teman, etc. And there I should mention also the pioneering work of Vishik and Fursikov in the deterministic setting. Right? So in the station, I mean, such a result was known for the incompressible Navier-Stokes system with conservative boundary condition. Here we have like non-conservative, compressible, and the result will hold. Well, in order to conclude, since I think according to the schedule, my time is almost up. So let's conclude. So we actually did not prove ergodicity. We proved very little. We just proved the existence of, say, stationary statistical solution that is sitting on any bounded global trajectory, on any bounded trajectory, in order to show that actually the measure is unique, or if you usually want to show ergodicity of such a measure. What is ergodicity? Ergodicity means that if you take a Borel set in the omega limit set, which the whole set is shift invariant, then it implies that the limit measure on this set is either 1 or 0. Right? Well, so what you can make sure is only that well, your limit, which exists according to the Kirov-Bogolyubov theory, is sitting on the convex hull of the ergodic measures on the omega limit set. So we are still far from asserting that actually such a limit is unique. So let me summarize the state of the art for compressible Navier-Stokes. So we have bounded trajectories. Well, if you have a bounded weak solution, globally bounded weak solution, that for sure generates a stationary statistical solution, which is a kind of Schiff invariant measure, which sits on the omega limit set. So there is a stationary solution, stationary statistical solution of compressible barotropic Navier-Stokes on each omega limit set of each bounded trajectory. I mean, we have the weak ergodic hypothesis, which means convergence of the ergodic averages on the omega limit set. However, we don't have it in general. And we can also show strong ergodic hypothesis, but it's only for energetic isolated systems where we know that all solutions tend to equilibrium. Okay, I think my time is up now, so thank you very much for your attention, and I'm ready to answer some questions if any.